Good evening, ladies and gentlemen, and welcome to this marine evening. It's October month, it's almost last month of the year, so this is our second to last marine evening that we have tonight. I want to welcome again each and every one of you making the effort to join us tonight. We have a very special guest speaker. We've worked with him before on a project that we have in front of us. We'll talk about that a bit later. And I also want to do a special welcome to everyone joining us tonight on the live stream. Please ask questions. We will allow your questions to be asked and answered after Mike has done his talk. So, for the rest of us guys, Mike is actually born in Zambia. He followed his father around from mine to mine, and that's where he got hooked on rocks. And around 1974, they made their way to South Africa. Mike is now retired. He is a local from Franskraal, and tonight he is going to share with us his passion for rocks. He's also a member of the Overberg Geoscientists Group. Mike, please come to the front.
On board, everybody can hear. Thank you so much. Thank you very much indeed for inviting me, Kari, and the team from Marine Dynamics. It's a real pleasure and an honor to be here. Kari actually thanked me, but I think those are the wrong thanks. The thanks should really go to Marine Dynamics, Wilfred Chevelle and his team, and Susan, who put a tremendous amount of effort and work into making the world a better place for all of us. And I think we ought to really thank them for this evening and the way it's been put together for us. The introduction of me was fun. I don't think anybody wants to know anything more about me. I think it's about the rocks that we need to actually talk. I'm a member of the Overberg Geoscientists Group, and as such, we're trying at the moment to sort of elevate interest in geology. We're trying to stimulate people's interest in the subject. We want people, youngsters, to come into the field. Geology is something that is a worthwhile career. It is recognized at the moment that we need geologists on the ground. There are 5,000 odd prospecting and mining rights lying out there, the DRME. Somebody's got to be the geologist to take all of those on board. So there's huge scope at the moment. It's a fantastic career. And we're just trying to excite interest in geology per se. Lay people are particularly, what does that mean?
No.
Lay people and kids are particularly the market that we're looking at, the type of people that we want to encourage. But that doesn't mean to say at the age of 90, like me, you could start a new passion and start thinking about rocks. I'm a little unfamiliar with the so please bear with me while I make all sorts of strange noises and what have you. It doesn't need anything more to say about this, except that our little team has grown from about 4 or 5 or 6 of us in the beginning, all the way through to about 64 locals in our Overberg region, and because we had to do it on Zoom due to COVID, it's now grown to about 120 people, and we've got a lot of people from overseas, especially old students and professors and doctors that are now studying and working and doing whatever they're doing in places like Australia or wherever they shouldn't be. But yeah, they're listening to us regularly. We have guest speakers and we talk to people often. We're busy with a number of current projects. I'm not going to bore you with all the details around about current projects, and we have a number of future projects that we are busy with, Earth-age displays. The display that we put together at APS is now being copied. People in Harold Porter Gardens, geologists under Dave Morant and John Bristow are now putting together a whole display there, copied on what we've done here. So we were the first, we did it right. Zambia have come to us and asked us now to do it over there for them. So I think we're ahead of the game as far as the rest of the Overberg is concerned. But let's get on to rocks. Let's forget about the old fuddy-duddies that are sitting around in an office somewhere. Normally we sit at the retirement office, the retirement haven in Hermanus, and we drink tea, and we have breakfast, and we discuss all of these ponderous matters that we have to think about. I don't know whether that guy is actually bragging about the size of the fish that he caught, how big it is, that thing that he's standing on, whether it's in front of the house, well, it's in front of the house that rolled down from somewhere, and whether he's bragging about his house was missed by that far, I don't know, but he's talking about something which I'm going to talk about. It's a rock. He's standing on a rock. And that's a very big rock, and it came all the way from up the top there. But no matter, even if you've got a handful of pebbles in your hands at the beach, each and every single rock has a story to tell. And that's what we're about tonight, is to talk about the story that rocks have to talk to us about. What are rocks? Where do they come from? How do they form? Where do they go to? What is a rock? Why do geologists walk around with hammers in their hands? It's not because they have this need to break rocks. That's sort of a convict sort of thing. Maybe some of them are guilty of that, but they need to tap things, and they need to find out how dense rocks are, and they need to find out whether they break easily. But at the end of the day, a geologist is a lost soul. A rock is a concrete thing. It's hard, it's put together, it takes effort to break this thing. So if a geologist hits it with his hammer, and it takes a bit of effort to break it, then a geologist knows that's a rock. So it's a very technical sort of way of finding out what he's looking at. It's not like sand, which is soft, and it's not like clay and mudstone. It's a real rock. Rocks are put together from grains, crystals. Sometimes they are grains and crystals. Sometimes they are crystals. You can see those crystals at the bottom there. Those beautiful quartzite crystals. There's a couple lying here as well. Amethyst is just another form of a crystal of quartz. Quartz is silicon dioxide. I mean, that's an easy one for me to remember, and that's why I like quartz so much, because it's easy to remember the chemical formula, SiO2. You see, I got that right this time. But that amethyst just comes from a little bit of tinting, a little bit of iron in the composition, a little bit of exposure to gamma rays, from a little bit of uranium that happened to be floating past, and then we get sort of that color. It can be clear, it can be smoky, it can be quartz. What's that stuff at ice? Rose quartz. You know, the beautiful rose colors that make lampshades out of, and all sorts of wonderful things. But there it is. The top my right-hand corner is a piece of sandstone, which I picked up on the beach, and you can see how useful sandstone is. It keeps the lid on my dustbin, especially when the wind is blowing quite hard. And in the other corner, you can see sandstone, which is cut through by cracks, which have been filled by quartzites. So that white stuff that you see on echelon cracking, filled by quartzites, hydrothermal fluids, which have deposited the SiO2 in there, and there it is. Rocks are not only made of one mineral. Normally, they're made of a hell of a lot of minerals together. Excuse my language. It's called an aggregate, and the aggregates are normally what we look at, and that just makes things so much more interesting. It gets so much more complicated. Minerals in granites or in other rocks that have been formed in place are referred to in situ as being in situ. In other words, they formed in place. And that is as opposed to rocks which have been weathered and carried about. So you have some rocks which, like in a pluton of igneous material which comes up from the earth's core, sits sort of in the crust of the earth. Doesn't go any further, doesn't get to the top, but it sort of sits there and it cools down and it crystallizes. And those minerals are then referred to as being formed in situ, in place, whereas weathering is a completely different experience. What we refer to we've got to start somewhere in terms of rocks. Where do they start and how does it work? So we sort of draw a picture in our mind of some kind of cycle, because everything is happening over and over and over again, and it all works in a sort of a cycle. So let's start with our igneous rocks. The igneous rocks are the ones that go right down there at the bottom with the magmas, and they are at 1500 odd degrees, and they will get pushed up in one way or another, and they will go through a crack or whatever it is, through a volcano, and they will be extruded outside. So they go up and are extruded onto the surface of the earth. You have sometimes the same sort of thing that happens, but there's that pluton that I mentioned. That's the fancy name for a lump of rock which has risen from the mantle and is now sort of not made it to the actual Earth's surface, but has slowed down, and as it progresses, it stops, and then it starts to crystallize. Called fractionation, and it's a specific sort of way that as it cools down at certain temperatures, certain things start to form. So certain minerals will cool at certain temperatures. And that's very interesting stuff that happens inside there. Thinking about massive one that we've got, the Bushveld complex, igneous complex, huge setup similar to this, where we've got 90% of the world's chromite and platinum group metals because of one of those things. Anyway, we've got the stuff that makes it. It's all coming from here. We've got the stuff that makes it to the surface. We have mountains that are formed, but we've got this guy weathering. So we have the igneous inputs, and we have some physical inputs, which are mountains, and then we have the guys that weather this all down. So acid in the air, acid in the water comes down, it washes away the mountain, it erodes that mountain, and it's all transported down back into, let's say for this case, an ocean, because it just makes it easier for me. But any sort of flat area that's on the surface, that's where this stuff will be washed down. Two, it'll get laid down in layers there, and eventually those sediments, which is the next stage of our rock cycle, the sedimentary rocks, get buried. They get buried deeper and deeper and deeper. They start moving downwards, so they start getting a lot of pressure on top of them, and they start getting back where it starts to get warm. With that heat and pressure, heating and squashing I called it, and the deep burial, you start getting rocks which start to change. Rocks that are changing are called metamorphic rocks. They're in the process of metamorphosis. Okay? I hope I'm getting shot by somebody. So we have the three types of rocks. We have the molten rocks, the igneous stuff. We have the sedimentary rocks, the table mountains. And we have the metamorphic rocks, which is the changing rocks. Okay? And we'll go through those stages. You see many of these different diagrams. I'm going to walk a little bit. I hope I don't get in the way or get hurt or whatever. But just different ways of saying very much the same thing. Some of these get tremendously complicated, but you have your gabbros, granites, dorites down here in your plutonics, down here in your core, your mantle, your molten stuff, all at very high temperature. Some of it makes it up through a nice big volcano and blows out. The igneous rocks then start to crystallize. Your rhyolites, andesites, and basalts are your lavas, which actually are being extruded in one way or another. You then have your sediments, which are transported and deposed somewhere within a suitable environment. And then you have compaction and cementation back of your sedimentary rocks. As soon as they get buried and exposed to heat again, they start forming different rocks altogether. So whereas you went from travertine, chert, quartz, calcite, whatever, you've now gone to conglomerate sandstones in your sedimentary rocks. Conglomerate sandstones, mudstones, siltstones, they get changed when pressure and heat are involved, and they get changed to things like siderite, argillite, schist, gneiss, marble, I can't read the rest over there, quartzite, greenstones, whatever. So you can see the names change, the compositions change, the chemical structures change, it all changes. But it goes then back again, because what happens when this all gets weathered off, you've exposed the metamorphic rock, that then gets deposited somewhere else, and the whole process starts going again. Or otherwise a nice big volcano pops up somewhere, and that process starts again there. Just to explain to you plate tectonics in action, if you've got a piece of crust over here, the Mohorovic line is over there. We've got a piece of the lithosphere, which is actually the oceanic crust, which is subducting below a piece of the continental crust. People often ask me, so these protons that you talk about, where do they actually come from? This is where it all starts. Because this stuff is going down into big heat and big pressure, some of the stuff starts to, with the help of the water that it takes down with it, which acts as a flux, that starts to pick up real temperature there. And so some of this breaks loose and starts to rise again. Big bubbles of this magma start to form again, and they start to rise up into the continental crust. They then get exposed as plutons later on. Okay, so we could have like a setting for the Malmesbury group, and we'll get to those shales that I'm going to talk about, the Malmesbury group, and the Cape granites. The Cape granites would be these plutons that are sitting there. And we'll see how they get into the picture later on. So as this thing moves, these things get hot, they move up, and they start making our croutons for us. If we talk about volcanism, we're talking here about a typical volcano, and we're talking about all sorts of things that are happening here actually that are associated with volcanoes. Volcanism is in actual fact the movement of igneous rock up a diatreme or a pipe. Gets blown out the top here. Some lava comes down, you get pyroclastics, which are all ashes and bits and pieces come running down the side of the volcano. They get buried. And they get buried by more. So what are they called? Sedimentaries? Yes, you get sedimentary tuffs, you get pyroclastic materials that are actually buried by their own weight of the further explosions, and they become sediments. So you've got igneous, you've got sedimentary stuff happening on the side here, you've got cracks which are formed and interact with groundwater, and all of a sudden you start getting this superheated water because it's at pressure, and it starts to pick up all sorts of minerals. Think about quartz, it picks up silica as it's down there, and it sort of makes its way to the surface, pops up through a crack, solidifies, and then you've got your quartz veins. And any other type of mineralization which actually happens at depth, facilitated by groundwaters, and taking advantage of all the minerals that are involved in the stuff that's coming up from underneath that magma. So quite interesting the way that this thing sort of circles within a very small environment as compared to the bigger rock cycle that I've just shown you. I didn't know at the time that we started. Could we just have a halfway check, please? Just give me a
We're at 10 to...
If we look at startup volcanoes, those are the nice guys. Those are the guys, Krakatoa and Mounts and Helens and these bigger guys that go pop. And when they go pop, people start writing headlines in newspapers about how they went pop and how big the damage was. But we get others like the Drakensberg that we had 180 odd million years ago, when that sort of thing happened. The typical example at the moment is in Hawaii, of a shield volcano with this crack in the ground, and the stuff just gently flows up out of the mantle and comes to the surface and starts to flow away. There are different compositions of these things, and there are different flow capacities for them. So the viscosity is different. Some of them flow difficult, high viscosity, and some of them flow easily, low viscosity. So we have here a low viscosity RR lava flow. And they called it RR overflow. That's not a mistake in my typing. It's the fastest lava flow that we've got. Typically, this is the one that'll come hurtling down the road at 10 kilometers an hour and cover a house and then just carry on. These hard, chunky, sort of very, very fast-moving lavas are quite dangerous, and things tend to get in the way of them. They fall down very quickly, and in some places they are quenched, and you get obsidian, which is like glass. It cools down like that. So these are your lavas coming up. They are classed in three different ways. You get basalt, which is an extrusive. You get the intrusive, which is your granites. And then you get the hyperbasal. Remember, right at the bottom of that rock cycle, right at the bottom there where the mantle was, the core was, those are your hyperbasal granites, your andesites, and those sort of compositions. If you then talk about Pahoehoe lava, also in Hawaii, it's a different type of lava. It's got a different viscosity, so it flows a lot slower, but it's a lot hotter. Up there, it's around about 1400 degrees sometimes, and it comes down quite rapidly in temperature down to about 600 or 700 degrees down the bottom here. But it's a very pretty lava. It makes ropey formations. It's the stuff that you see flowing into the sea that drips like this. It's extremely pretty stuff. It's not such nice stuff to pick up, though. It can be quite dangerous. It cools reasonably quickly, and there's a lot of stuff that happens in terms of the mineralization that we get from these lavas. The sands that it makes are black, so you don't go to white beaches there. This is the Pu'u'o vent in the Kilauea volcano from Hawaii. Don't know why they've got names like that. Pillow lavas are formed typically undersea, where you have a mid-ocean ridge where plates are moving apart from each other. You're going to get a crack. And that crack is, you will get basaltic lavas flowing up that crack, and they will start adding to the actual seafloor, and they will start spreading that seafloor apart. And when those basalts come up, they make little bubbles of lava. And because they are quenched so quickly by the seawater around it, it almost immediately freezes the outside of that lava and it falls off as a pillar. And you get millions and millions of these things laid down. That was the best example that I could sort of find of a pillar lava, but we've got brilliant examples in South Africa, in the Barberton area as well. And these pillars are around about 1 meter wide, but we've got 3 or 4 meter pillars. So it just shows that basaltic lava was actually coming out quite quickly from the seafloor at Barberton in the old days. 3.2 billion years ago, somewhere around there. Okay, we've got the rock forming minerals. Now, here's where it starts to get highly technical. So I'm not going to spend too much time on this. Those of you that know these things, bear with me while I gloss over them, because to get involved now, we can spend the next 10 years discussing this particular slide. But the rock-forming minerals are basically olivine, pyroxene, amphibole, feldspar, mica, quartz, and those are the silicate rock-forming. There are others. There are carbonatites. There are all sorts of other minerals that help. But this gives an idea of the type of thing that we're talking about. There are colorings, there are conchoidal fractures, it breaks in a certain way. There are ways of actually finding out what this is all about. They've got beautiful names: andesite, augite, hypersthene, dioxide. That's the pyroxene group. The amphibole group is a different thing altogether. Funny enough, amphibole is a rock-forming mineral, and when it's been metamorphosed, it's called amphibolite, and it's completely different. So yeah, I don't know why they do that to us. Feldspars, a lot of the Earth's crust is formed, and I'm talking about the crust, not the basalt ocean floors, formed of feldspars, about 60% of it. Yeah, I'm not going to go through that. Mica, everybody I think knows mica. Mica is that sort of clear to black plating material, which you can sometimes use in irons and whatever for insulation. It makes a perfect cleavage. It's absolutely clear, breaks into thin sheets. The mafic mica, which you get in granites and that sort of stuff, which is black, is different to the other one, which is called, affectionately called muscovite. It's called muscovite because in Russia it grows into plates, yay big, and they use it for windows. You can actually see straight through the stuff. It's a mica, it's a rock, but you can cleave it to within a thickness of about 3 millimeters, and you can put it inside your window frame. Makes a perfect window. So it's affectionately known as muscovite. Quartz, I think I spent a lot of time already talking about quartz. One of the felsic granitics. It's one of the last minerals to form. It forms at about 700 degrees, so it's one of the cooler minerals. It forms very much later than some of the pyroxenes and olivines that form very early on in the up to 1200 degrees. There's a typical granite there. If I'm confusing people with mafic and felsic rocks, the discussion really is some rocks are more magnesium and iron, Fe, iron, ferrous composition of igneous rock than a typical iron silica rock, which is a granite or a rhyolite. Okay, and it's got to do with acidic or alkaline type of rocks as opposed to carbonatite rocks. It's the way that a lot of the lavas are actually classified. People look at it and say, well, that's a felsic or that's a mafic rock, and it just depends on that alkalinity acidity. It almost immediately starts to point us into which direction you're talking. Is it a magnesium-based or a calcium-based? Where do we go with the chemistry as far as these rocks are concerned? We're looking at granite, and I'm spending a bit of time on igneous rocks because these are where all of our good stuff, all of the minerals and these sort of things come from these guys. They come from inside the earth, and we need to spend time on them. Granites look very different in many cases. This is what we find here around about us. Intrusive granites, mainly plutons, probably down there towards Pearly Beach. I think I've got a slide. Yeah. Let me just go back again. So in granites, if we've got a granite in our hand, go down to Pearly Beach, pick up a granite and say, okay, so I know I've got a granite in my hand, but it might not look like that. But it does have plagioclase, the orange stuff in there. It does have potassium feldspar are, the whiter looking stuff. It does have biotite mica in there, the dark stuff over there. It probably has a little bit of olivine as well. You can see the quartz within that. So you know that this rock is basically made up of a few different things which you can recognize, basic indicators. And you know you're sort of sitting with a granite. It's an igneous type of rock. Let's not call it a granite yet, let's call it a granitoid, because it's sort of similar, but I need to go to the books and understand why it's a granite and not something else. Did you know that the Statue of Liberty stands in a granite plinth? So it's not always enough to say that I've got a granite in my hand. This is just an indication of how things cool down. I was talking about that fractionation process of crystallization, when you've got this stuff under the ground, and it's easiest to understand that if it's in this nice chamber under the ground, it's insulated and it starts to cool down at certain temperatures. And you will find that olivines will tend to crystallize first at the highest temperatures, and there's your quartz down at the bottom here at around about 600 or 650 to 700 degrees. So your quartz is crystallizing out at the last stage. It's a Bound's reaction series is just a diagram that they use in order to determine which part of the process are we in and how old are these rocks. In some ways you can almost date them this way. What should it be for me if we know that these were deposited 550 million years ago? Where should we be in this discussion? It should be granitic, or it should be maybe andesitic basaltic. Okay, so it's just another help way of doing this. This is a bit of a comic slide. I went down to where was it? I went down to Franskraal at Burley Beach. There's a huge pluton there. It goes way offshore. And that pluton of granite is sort of placed at the same time that the Hermanus pluton up in the H&A Valley was in place. About the same time as the Sea Point granites, about the same time as the Simonstown ones, and Pop. So we know that it was in place more or less Cambrian about 550 million years ago, and it was moving up through these Malmesbury shales, which are our bedrocks. And there it is at Burley Beach, and you can go and have a look at it. And I took my hammer along and smashed off a piece. No, I didn't. I just went and had a look at it, and I didn't touch it. There are these beautiful crystals of tourmaline, big tourmaline crystals within this granite, and makes it quite unique. But you can see, there I've got the feldspar, there I've got the quartz, there I've got the biotite. So I'm looking at some kind of granite here. And it makes it easier for me to identify in terms of granites. But having gone through the checklist in my mind to say, okay, so let's go through classification, definitely a rock. It took me my hammer, yeah. It's definitely igneous rock, because it's got a certain shape and a look to it. So it's a normally crystalline, because it is normally crystalline, it's right there in front of me. And it's a very coarse-grained crystalline rock, so that I know it's probably come from plutonic. The coarser those crystals are, the longer it took to cool down. And that's why it would be a coarse grain, and I can make the assumption that it would be maybe a plutonic as opposed to something that's been spat out into the air. I know that now I'm looking at something which is a granitoid, because it's got all those nice things. So I say it's a granite, sharp. I can put it down now, I can walk away, and I know that I've got a granite. This page is about 4 times too short. In actual fact, we're dealing here with a Muscovite biotite granite. That is that particular formation, and it becomes quite difficult, as I say, 4 times this to choose which one you're actually looking at. So be careful when somebody walks up to you and says, "What is this?" Be careful, because you might say to him it's granite, and he might say, "So which one?" Good luck with that. Anyway, yeah, it's great fun collecting these things. It's also great fun sitting at night and having to go through this rock to see particularly what it was. We spent a lot of time on the igneous rocks. Let's get to the subject of the draw tonight, the sedimentary rocks. I didn't say that, did I? But this is our favorite. This is what we are all exposed to every single day. The moment we look at the mountain outside there above Academia School, we know we're into the sandstones and we're into sedimentary rocks. That's what makes our life exciting. Every time we look at that mountain, we understand there are folds there, and if I'm ever invited back again, we'll maybe one day get to discussing why the folds there and why those mountains are there and how they happened and where the tectonics were that pushed them up, etc., etc. But there are our sediments. Those are the Table Mountain Sandstone Group. They were overlain by a diamectite, a puck-basalt, and in some places in Maclear's Beacon, it's still there. You can still see it. I'll show you a picture of it just now. But that tillite still exists, and it exists in the southwest corner of Betty's Bay. There's good exposure. There's another exposure in what's around the corner there. At the end of the day, it's all laid down on Malmesbury Group rocks. So let's look at a bedrock. You've got a bedrock. It's called Malmesbury Group. It's a shale. It's a ignimbrite. In other words, it's old pieces of old lavas and ashes and tuffs and all these funny things. And they've all been modified because it's been buried and it's been subject to great heat and changed all over the place. That is the base rock. Through that came these prutons of Cape granites that I talked about, okay, in all those places that I discussed with you. So the Cape granite is lying underneath here, okay. It's involved with the Malmesbury Group by pushing through it, and there's a small formation there which we won't talk about, but it's also a sedimentary layer of the Grafwater Formation. What's more important are what used to be 7 kilometers of sandstones that were laid down in the Agulhas Sea. Around about Ordovician Silurian time, so around about 500 million years ago. And we've got a kilometer of it left. It used to be part of a very, very big mountain. And that's all we've got left. Because it is so hard and it wears so evenly, we've got a nice bench table of it. Normally your sandstones will form cliffs or mountains because they're so hard. And that has been eroded away. So there is what we are interested in. The sedimentary rocks, there are many types of sedimentary rocks. But in actual fact, how do we classify these things? They are broadly speaking 2 different types of rocks. We've got clastic rocks and we've got non-clastic rocks. So clastic rocks are the bits that have got bits and pieces in them. They've worn off somewhere and they've been rolled down mountains and they've been deposited in nice flat beds for us to discover. The non-clastics are a little bit more different. They are organic or inorganic materials which have been deposited out of solution or chemically deposited in one way or another. So if you had diatoms floating in a water column such as the sea, and those diatoms their body parts were composed of silica, and those will drop to the bottom, that chemical binds together, and that becomes a sedimentary chemical rock called chert. So that's the difference, where one has been washed off and one has been formed differently. Limestones are formed, so they are not washed away and washed in there. They are chemically bound.
Mike, sorry.
Go for it.
2 of you guys is going to remember this night for the wrong reasons. Your lights is on. CEM 44206 Audi and 29938 Hyundai. Kets. Nobody?
No one.
Okay, then it's fine. Then you can carry on. Sorry, Mike.
Good luck. I'm not helping to push. Okay, so the classic ones, I think I've just discussed now. They range in size from boulders, big jobs, down to pebbles and cobbles and gravels. And your clays are the very small ones, very, very fine ones that actually are lying in nice little plates. And they're around about a 16th and less of a millimeter, so 0.003 I think is the measurement that we look out for the clays. The mudstones, the sands, conglomerates, and volcanoclastics. I was talking about tuff or ash, which is laid down as a sedimentary rock from a stratovolcano on the side of it. Because it gets buried and it gets hardened, it gets liquefied, it gets turned into a rock, it becomes a sedimentary rock. And the same is going for cinders, which is from that. It actually travels in the cloud above the volcano. It's deposited very, very far away, falls down as cinders, and then becomes a lithified unit to be called scoria one day. 2.1 billion years ago, banded ironstone started to work. It's the red one is the jasper, which is the iron-rich chert that I talked about, and then we've got iron. Oh, that's a nice trick. Then we've got the iron quetchert layers, which is the grey one lying in between. It's a bit difficult to see on that, but you can see that definite banding inside there. So when did oxygenation turn iron into rust? Around about 2 billion years ago. That's the great oxygenation event which killed off all the non-oxygen eating bacteria. That's another discussion. Anyway, so those are the chemically laid down ones. I think I need to try and just find them. Okay, so we've got sedimentary rocks, the two basic classifications of them, and then where do they come from? They get washed off, as I said, they weather off the top of mountains and this sort of thing, in most cases. And those are the ones that we are particularly interested because they tend to influence us a lot. They form the rich farmlands and these sorts of things. But they can be carried by wind, water, or ice. Okay, remember diamectites, remember tillites that I talked about lying on the top of Table Mountain. Those are glacial deposits, and I'll show you something about that. The fragments are abraded in that process of being transported down the sides of mountains, so they become rounder and rounder, and you can actually determine at one stage or another how far it's been transported, or in what form it's been transported, what it's been transported by, because of the abrasion of those particles. This just happens to be a great exposure. Remember the Table Mountain photograph that I said, and there was a white line on top, which was the diamectite, and on top of that again, there was this lot was deposited. It's now worn off Table Mountain. But if you stand at Copperbelt in Granites in the Cederberg, you will actually see this profile. This, if you can imagine, that was maybe the top of Table Mountain, that was lying on top of it. And that is a sedimentary sequence which is called the Bockerfeld shales. And they are grouped together under a group. And that group has all got different names for all of those individual sedimentary events, such as Blindbelt, Karoo, Osberg. Imagine the guys overseas trying to figure this little lot out. It must be a nightmare, but those are the official names. And so some guy in Scandinavia would Osberg. Yeah. So that's the way we talk about them, and those are a very clear indicator of exactly how pretty those formations are. And you're welcome to go and look next time you're standing on the top of Copperbelt. How do they become rocks though? Okay, so we've had all this stuff washing off, and we know that it's channeled. For simplicity, I've taken one that just is basic. It's a mountain in the background there. It's a river which transports, so everything gets washed off the top there, it gets transported into a sea, and it starts to get laid down. There's our beach. Sedimentation and deposition, nice and loose, lots of holes between the pieces and the particles and the bits and pieces. And then it starts to get buried by the next sequences that come down off the mountains, and you start to get gravitational compaction. So compaction starts to happen, and the interstitial gaps start to get less and less and less. Okay? So your compaction, gravity, there's a little bit now we're going to get buried further and further and further. So this lot is going down further and further into the crustal area. It's getting heat, a little bit of heat from the bottom, getting a little bit more pressure. Now it's beginning to be cemented. And we have common cements that work with this kind of sedimentation process. We've got quartzites, we've got clays, we've got a number of others, hematite and limonite, which are not so common in our area, but we're talking more about the clays and the quartzes and the calcites, especially in our area, because the stuff that we're used to. So that's how it happened. Gets buried, gets pushed together, and then gets chemically welded, if I can put it that way. I'll be back to my dustbin with it again. So mudstone is very common in our area. A lot of Bockerveld around Caledon and up on those beautiful hills at Caledon. In the cuttings, if you drive through the cuttings, you get those beautiful purple, mauve, red, black, white mudstones that are in there. Take your geologist hammer and go smack that and it sticks inside because it's not hard. It's 400 million years old, but it hasn't hardened properly. Okay, because it's a mudstone. It's a different type of stone altogether. It's actually stone, but because it gets water and it goes soft, and the plates tend to slide on top of each other. Those tiny little crystals slide on top of each other. So those are the very pretty mudstones that we get. Think about the road between sort of Beaufort, West and Lensburg. Those cuttings there are also mudstones. They just have a different sequence, they're a different group. They are the Karoo group, but it's a similar type of rock that's been formed there. Okay, so it's a very, very, very fine clay that's been lithified and made into a mudstone. Finely layered marine mudstones called shales and windblown mudstones called loess. So there is a difference when we're looking at these things to sort of say to ourselves, okay, so some are marine sequence and some are aeolianites. We've got a lot of aeolianites in our area. Aeolianites being the windblown stuff. These tend to erode away fairly quickly, but they give us the food, they give us the fertilizer for our beautiful wine grain areas, our very, very fertile valleys where we can grow just about anything in. And just for interest, the Curiosity rover found mudstone on Mars. And what's more, it is actually carbonaceous. It contains organic substances. And I think they toluene and propane and benzene. So think about that one. That's quite interesting stuff that's coming from out of our planets. Sandstones, mostly formed by quartz. Most of our sandstones that we are used to are formed by quartz. You get different types of sandstones. They are named according to compositions. So we will have mostly arenites in our area. Arenite is a quartzite, mostly quartzite and very little other minerals. Hence, nothing grows in it. It's not a rich sort of nutrient-full type of sandstone. Arkose sandstone's got a huge amount of quartz in it, but and feldspars, but not much clay. Grey Wacky, I love that name, is a sandstone with a clay matrix that's got a little bit of quartzite, and so you go through all these various names, and they get classified by how much of each component they've got in it. And it's very useful for my discipline. If we carry on amongst the sedimentary rocks, this guy is actually bragging. I don't know if it's the same guy in that first picture with his big rock, but he's got a section of Witwatersrand from Conglomerate there. Conglomerate is stuff, big stones that have been stuck together by a sort of a flower or whatever is in between there, sticking it all together. It's been laid down, it's been compacted, been stuck together, and he's got something from about 2,000 meters down, 2 kilometers down in the Witwatersrand group, those conglomerates. Very, very pretty. We're more used to this sort of thing. We've got little, tiny little casts, let's say about the size of my thumb, first thumb there, and it's more or less stuck together with bits of sandstone and that sort of thing. We know our calciums, we know our quartzites, and we know our class sizes. You can see some of them are regular, which is telling us that it hasn't been transported that far. Some of the material is rounded, so it's coming from a bit further away, and it's all landed up on the same sort of delta, and it's been concreted together. I told you about the tilites. There are 2 tilites that we are used to. This one is outside Beaufort West, sort of beneath that Karoo sequence that I talked about that formed in the Foreland Basin, which was formed after our mountains. The Dwika tilites, you will see the clasts inside there, pretty irregular. There's a 50-cent piece, pretty irregular size. These things are picked up as that glacier moves along. It grinds along the surface and it forces those rocks into the ice. The ice then picks it up. And as it's grinding along, it's grinding around this flour up as well. It sort of makes a flour out of the rocks as it progresses over the rocks. And all of that flour and these rocks and everything is picked up. And eventually, as the temperatures change with climate change, which man didn't cause because it was a very long time ago, it's exactly the same things happening now. The glaciers tend to melt and they drop these stones. Amazing. That's called a drop stone. They drop these stones and the flour gets dropped around the stone. It then gets sedimented over by other stuff. It's a sediment itself, so it gets consolidated, and it is called a tilite. The Pakos tilite happened around about the sort of same time, 340 million years ago, sort of beginning of the Devonian. So did the Pakos tilite, just in different places. These were around the Cape Mountains, in amongst the falls and what have you. There were these huge glaciers and they were being picked up. This is the stuff you'll find in Bringle Bay, Betty's Bay. Typical example, very much smaller clasts. Those are around about, I would say, pea-sized in the examples that I've seen down there. And the size that we've got there is about yay big. That's in the Dwika. So the Dwika stuff is substantially bigger. Very much thicker glacier, 2-3 kilometers thick. Okay, so we're looking at different types of things there. But also sedimentary rocks at the end of the day. If we go down Clarence Drive, how are we doing for time? Halfway?
44 minutes so far.
And I'm on 23. I better start moving. If we go down Clarence Drive, we can see more sediments, Table Mountain Group. little bit of scree boulders that have been reworked by beaches in times of transgressions and regressions of glaciers, so that the sea levels were much higher. They've reworked those boulders into nice round boulders, as our sea is doing at the moment. And we've got the Malmesbury shales exposed. Do you see the car up there on Clarence Drive, right there? No, you can see the manganese. That's the manganese, but there's the car over there. So that car is actually travelling along, there it is. Now you can see. If you take a shot with a drone towards the drive, you can actually see that base rock that I was talking about. The Malmesbury shales are actually exposed there. And you can see the sandstones that we love so much, that form our beautiful mountains, are lying on top of the Malmesbury group. We have a problem. It is 600 million years old. Shoot me if you know the right ages, because I'm rounding off just substantially. And we've got 400 million years. Because it's lying on top of each other and there's nothing in there, there's 200 million years missing there. We call it an unconformity. It's lying unconformably on top of the other one. Because of that hiatus, we don't have that. We've got no rock there to say, okay, we can date that rock exactly and say it was laid between two of them or before it or after it. There's nothing there. You can't see anything at all. And there's some beautiful examples down here at the Caldas Hotel that I take people to go and have a look at. But that unconformity is just about the gap in time. If we could drill straight into that, we'd probably eventually get to some kind of formation which we could date and say, okay, so that came in between the two of them. Right there, can't see it, we call it an unconformity, and we're very happy. The stuff that we used to, right here, where we live, man, we've got some beautiful sediments here. Sedimentologists go crazy about it. John Malone mapped this in 1984 and still comes here. He's been in petrol, he's been in all sorts of sedimentology. He comes back here for refreshers because it's so good. We've got some of the best aeolianites in the world right here. We've got the Caldas Cave. I'm not talking about the paleontology. I'm talking about the rocks. So the inset that I put in is the Walker Bay aeolianites. Those are the wind-blown sand dunes that have been deposited on top of each other down the road here. And those have been deposited on some Durbanville formation limestones. Those limestones that you walk on, those are formed out of shells, that they are pieces of shell that have been cemented together. And there's an unconformity. Guess why? Paleozoic Table Mountain group coil sites, 440 million years old, 2 million years old. These are all quaternary. So those quaternary Holocene, Pleistocene sort of age groups in there are lying on top of those very old ones. And right in there is a conglomerate. We talked about a conglomerate. I'll show you the conglomerate. It's called the Bedrock Formation. There it is there. And if you go and look very careful next time you're down in the Caldas Cave, you will see that conglomerate lying in here. It goes all the way around. And if you walk to the Caldas Hotel, you will still see it if you look carefully at the same level, the same height as in tight locality, Bedrock River. That's where the best examples exist. That's where these names come from, by the way. The Hoop, Flavanus, Krans, and what have you. They are type locale for that rock. And it is the best example that you will find. You will see it in that area. Okay, so you'll see the best of those in Varnas Krans. Nonsense, but better ones. Jean. Okay, so I'm getting a bit carried away, but that's exactly what we've got here to be very proud of. I've talked about I've got this thing about people doing houses in strange places. See the undercutting there? What's happening in the Caldas at the moment, where the cracks have formed and the sea is falling. It's falling into the sea because the sea has undercut those very, very soft aeolianites. I think that guy feels comfortable if he comes down here and looks at the size of that thing that's happening there. I must stop being like that. I've done the sandstones. I'm going to wrap up pretty quickly. I'm sorry to do this to you. But we're getting on to the last section now, which was the metamorphic rocks. The metamorphic rocks are the ones that are changed. Burial, heat, pressure, interesting facts. Mponeng mine, the gold mine, deepest, about 4 kilometers. The rock at this level is about 66 degrees. It should be at about 100. But because of a lot of things that I could explain to you, we don't have time tonight, it's a lot cooler. But that's substantially warm as it is. If you go down a hole and big rocks, and that's the temperature. They pump about 6,000 tons. It's a slurry of salt and ice. They pump down the mine, huge fans, blow it down the adits, so that the guys get the temperature to at least something that's livable down there. It's very, very warm. Thank goodness it's not 100 degrees like it should be. Metamorphic rocks form when subject to high heat, high pressure. Hot mineral fluids, remember the hot mineral fluids we saw with the stratovolcano, with the mineral, the magma and the groundwater? Those are the hot mineral fluids that I'm talking about. Those are hydrothermal fluids, okay? Some combination of all of these factors. That's how we get metamorphic rocks, okay? Conditions like that are found where the tectonic plates meet, bang, or they subduct, and things start to happen. All sorts of changes start. They are valuable rocks. Michelangelo had a thing about marble. So it was a very valuable rock to the Greeks in those days, still is to us for other reasons. Abrasives, carborundums are metamorphic rocks. Talc is used in cosmetics nowadays. You say you're actually smearing rocks on when you do that sort of stuff. But yeah, there's a lot of uses for the metamorphic rocks. Gemstones, gold, diamond, metamorphic rock. Okay, carbon, heat, pressure, sweet zone, right at a certain place within the mantle of the earth. Right there is where diamond forms because of the heat and the temperature. We can talk about that as well. But here we have the changes. We have slate, which has been formed from mudstones. So it's been subjected to all of those things, and it's formed into slate, which cleaves very, very nicely because it forms along those very flattened, which were to start with clay, so they were very flat anyway, but now they cleave much easier because it's been hardened for you. Marble, which comes from your stuff that we walk on, lost my train of thought completely now. The dolomites and the limestones, which are subjected to the same sort of thing, and it changes into marbles, and is usually striated for many reasons, but it's got to do with having other stuff in between. So those striations also altered. Where it's very, very pure, it's a different type of limestone. Like chalk is a limestone, but it's a very pure type of limestone made out of a certain type of animal. For instance, I think it's here's some. And there's a guy standing on gneiss. Gneiss is basically granite, or volcanic rock, which has been reburied, turned around a little bit shaken by what happens down there at those temperatures and pressures, and you get these beautiful wavy lines. This is Sand River in Limpopo, and as you can see, it goes on for a long way, and it's all around there, but he just happens to be standing on a very, very nice piece of gneiss down there. There's a quick chart. I hope these guys don't see this because thank you very much for Matrix, and I must give thanks to all of the guys that I've actually stolen material from over the internet. I must give thanks to Bruce Cairncross. I must give thanks to Professor Bruce Cairncross. I must give thanks to Jean Milan, Dr. Haley Korthra, Dr. Who else? Ben Clark, Ben Clark. I've literally taken some of their diagrams and put them in here, and it's not my stuff, it's their stuff, so please don't shoot me. I apologize. It's in the better for the good. Shales and mudstones, which form slates, phyllites, which is just a different type of slate, also formed from those. Shales, granite, volcanic rocks, which are forming gneiss, which we talked about. Marble, which is limestone and dollarstones, or dolomites, where I got stuck just now and I lost my train of thought. Sandstones, forming quartzites. That's an interesting. Sandstones that we've got here, looking at the mountain, get compressed into solid quartz. Okay, that very, very hard material. And then hornfels. Hornfels, if I can think of an example of hornfels, the best example I can think of is Durbanville Quarries. Just outside Cape Town, they have those huge quarries which they use for road filling material. Very, very hard, durable sort of rock. And what it was those shales which were already metamorphosed rocks. They were shales and mudstones that have been already changed by heat and then got reburied and even further processed by the heat and temperature. And now they mine them out in that area for this material which is hornfels. So hornfels is a particularly sought for sort of rock because of its nature. It's pretty hard stuff. Some interesting sort of metamorphosed rock, and there's a piece of it down here as well. That unakite is, I collected some when I was up in. That's a carbonation of unakite that we polished. up in Messina. So it's just a epidote and orthoclase which has been pressed together and looks very pretty. We have Mudstone called African Jade sometimes. It's a folded green chert. Remember we talked about chert being a sedimentary rock which comes from animals which have died and gone to the bottom of the ocean and have been cemented together. But this one has been metamorphosed, so it's been changed. It's been put under pressure, it's been turned over, and you get these beautiful green bands within green bands in that African jade. That's leopard rock over there. It's not leopard rock, the golfing place. That's our leopard rock that we talk about. Very, very pretty serpentinite. All of these serpentinites, things like soapstones and what have you, all easily worked, made up into carvings and what have you. Amazing names: lizardite, chrysotile, and diorite. Chrysotile is what's responsible for asbestos at the end of the day, and in some modified forms it turns into tiger's eye as well, with a little bit of tinting and a little bit of additions of iron and whatever else was put in there. So where is our journey actually taken us? I'm wrapping up. I'm sorry, we're going over time. Where has our journey actually taken us? We have been visiting the metamorphosed zone of Cape Town, of our whole area underlain by those Precambrian time. So more than 600 million years ago, those Precambrian slates and shales and mud rocks that were changed into the Malmesbury group, which were intruded from underneath by the Cape Granites, about 500. This was, we're talking here probably just before Cambrian times. They intruded into those Malmesbury group. We've had a look at the Igneous Rocks, we've had a look at the Metamorphic Rocks, and then we've gone to our stack of things that we love called Sedimentary Rocks. The Sedimentary Rocks, we've got the Peninsula Formation, and we've got another set of the Table Mountain group, which is Ordovician Silurian in age, anything like 500 million years to 345, maybe a little bit more than that, maybe 365 million years. We have all of these sedimentations of basically quartzites that came off mountains and were washed into a sea and formed these beautiful mountains that we have today. The pacastelites we've talked about as sedimentary things resulting from icebergs and glaciers that were left behind. The Cederberg I haven't spoken about, but it was really also a glacial event that is sandwiched between that huge set of sandstones and that set. And those shales in there were as a result of all of those glaciers melting and leaving behind a freshwater sea where you didn't expect one. So we were surrounded by saltwater seas, but there's a freshwater sea. A lot of vertebrate, what do they call them? These bugs that walk around, trilobites, all captured inside the Cederberg Formation. There's some Cederberg, no, there's Copperbelt. There's Copperbelt brachiopods here. But the brachiopods are the shells and things that were left behind that were captured in that little group there. Then we had the Nardo group. We haven't discussed the Nardo group yet at this stage, but it lies on top of our mountain at the back here, right at the top where they into those monkey stone rocks. That's more or less Nardo that you're looking at. So if it's got that really rough monkey stone look to it, that's probably a Nardo sandstone, as opposed to the very hard sandstones, that grey, that super hard stuff that we see very often at the base, right at the sea here. We've talked about the Bockerveld. Those were those beautiful exposures that we saw, our marine sequences, all of them, and different stages of deposition within a marine environment in the Devonian about 400 million years ago. And then we get all of a sudden to our own little Bredasdorp group. Hello. Our Bredasdorp group is what we walk on every single day of our lives. Go down to the dunes. That is the Strandveld part of the Bredasdorp group. It's the youngest, so it's happening right today, Holocene. We then go from there to Barlows, which was those beautiful aeolianites, a windblown sequence that I talked about. We go underneath that, we get to the, name has escaped me at the moment, the Banku Formation. Banku Formation being a marine terrace sort of area. Below that, we would have had the claimed conglomerates forming, and below that, we would have had the De Hoop Vlei, where I've just spent the weekend in the pouring rain trying to look for prehistoric fossils and getting very wet in the process, but we had to do a work formation, which is the base formation of our beloved Bedrock group. Okay, so that's what we've been in a very, very quick look at rocks tonight. I'd like to introduce Nick Norman, retired geologist, got into writing, started writing books, a great number of books, geological journeys, geology of the Breton Track, Box of Rocks, Extraordinary World of Diamonds. So he's been quite prolific in terms of what he's produced, and he's very kindly given us a couple of, one of those boxes to donate with his book. John Bristow, Dr. John Bristow of the OGG, put him under pressure to donate a number of those books, and we got Barry Bryant to put the box together for us to make the samples and put the whole lot together with the help of our sponsors. And John Bristow managed to get everybody together and produce that box of rocks, which is a sort of a collector's item. They're not common. I believe that Marine Dynamics has some to sell. And if anybody can't get them here, they can get them maybe directly from me, or they can contact me. And I think the better thing is for me to put them into Marine Dynamics and let you take them off Marine Dynamics' hands. So that box of rocks is the result of quite a bit of hard work by the OGG just to try and make something for children and interested adults to have a look at and say, here's the book which describes it much better than I could ever try and do it. But it's got all of those elements in there. It's got the rocks there. It's got a little hand lens there for you to have a look through at the crystals in the rocks. And I encourage you to have a look at one of these box of rocks. It's time for the lucky draw, and I think you can do that for us. Would you like to stand up and do that? And I'm going to say thank you very much for your attention. And if there are any questions, I'll try and deal with them after we've done the draw. Thank you.
That was very interesting. Just before the lucky draw, I just quickly want to mention to everyone that's joining us online, unfortunately, the live chat has been disabled because we've made this video safe for kids to watch. And with that feature on, no one can comment. So if you have any questions, please afterwards, this video will be published and you can publish your questions there. Okay, so now for the exciting moment, guys. Please reach underneath your seat and feel if you can feel something stuck there. Apparently it's on the side, not so much underneath. Like there's a little ridge. Any luck? Congratulations! Please make your way up to the front. You're going to head over. Just show the camera what it looks like, right?
I'm sure you're going to have a lot of fun with this box of rocks. And maybe we should show the camera who's actually winning your box of rocks. With compliments from the OGG, the team at Marine Dynamics, and Nick Norman in particular. All the details in there. There's a book in there and a whole bunch of samples for you to amuse yourself with the next 25 years. It's a pleasure.
Should I give him another hug?
Another hug? We'll do this as long as it's necessary. Are you finished it? Thank you so much. Thank you.
Well, thanks again for being our guest speaker tonight, Mike. I think it was very enjoyable. I mean, who doesn't want to learn more about rocks? And the even better news is this won't be the only time that Mike will be one of our guest speakers. Next year, we will schedule him into the setup or the schedule as well. Again, so prepare yourselves. If you want to quickly review what was said tonight so that you're on top of things next time Mike speaks, like I said, this video will be published on YouTube under Marine Dynamics Shark and Well Tours, our events playlist. Alright, so then I want to thank for tonight's food, which is the delicious soup and bread rolls, the Great White House for preparing this. Thank you to Susan. Thank you to Marine Dynamics for hosting this evening. Guys, please, I want to remind you to go and visit the African Penguin and Seabird Sanctuary to visit the penguins, but also to visit the nice geo trail that we have there with even more information. And remember to send all your friends and family family to visit us, whether it's going on a boat for a Vereenig 5 tour or joining our shark edge diving adventures, or even just dragging them along to the Penguin Sanctuary for a nice cappuccino and cake. Please support us further. And once again, thank you for being here tonight. Your cover charge is going to support the Dyer Island Conservation Trust. And if you want to learn more about the work that we're doing with the Trust, you're welcome to visit the website, which is www.dict.org.za. Okay, I think that's it for tonight. We're just in time before the lights go out. Don't worry, we do have generators, so you will be able to see which soup you are going to choose. So, thank you.
Thank you very much. Oh, all right. The best side.